Hi, everyone. I wanted to go through FRQ from the AP Bio exam that uses standard error and 95% confidence intervals. You can look at this one more time so you can feel completely confident with whatever the College Board throws at you with regarding to this question. So let's take a look at this question. Yep, let me find this here. That's not the screen I wanted to share, sorry. Share screen. We are looking for right here. Okay, this was the 2014 AP Biology exam, question number 1, which is the first time they ever put 95% confidence intervals on the AP exam. So the question read as follows. Trichomes are hair-like outgrowths of the epidermis of plants that are thought to provide protection against being eaten by herbivory. In a certain plant species, stem trichome density is genetically determined. To investigate variation in stem trichome density within the plant species, a student counted the number of trichomes on the stems of 6 plants in each of 3 different populations. The student used the data to calculate the mean trichome density, number of hairs per square centimeter for each population. The results are provided in the table below. So here's population 1, 2, 3. These are the 6 plants. Here's the mean for each population, and here is the standard error, the mean for each population. Now, this question was written before calculators were allowed on the exam, and notice they kept the numbers really super easy. You will not be asked to calculate standard error, the mean, on the AP Bio exam, but you do need to know how to apply it, which is what they're asking you to do in this question. So part A said, on the axes provided, create an appropriately labeled graph to illustrate the sample means of the 3 populations to within 95% confidence. And they told you 95% confidence is sample mean plus 2 standard errors of the mean. And on the next page, this shows you what the template provided they gave you to do the graph on. So we're going to switch screens for a second, and let's go ahead and show how you would do this graph. So I hope you guys can all see that. So we have 3 different plant populations, okay? And since there's 3 different plant populations, the most appropriate graph would be a bar graph. So here's population 1, population 2, and population 3. Okay, and for population 1, the mean is 9. For population 2, the mean is 14. So let's scale this 1, 2, 3, 4. This would be 5. And I think it was trichomes per centimeter squared were the units on there. Okay, 1, 2, 3, 4. Here's 10. 1, 2, 3, 4, 5. And here is 15. So for population number 1, the mean was 9. So that would look like that. For population number 2, the mean was 11. So that would be right here, for example. And for population 3, the mean was 14. Okay, so we have our means, but now we need to put our 95% confidence intervals. And the standard error, the mean for all 3 was 1. And to get the upper limit of your 95% confidence interval, you start at your mean and you add 2 standard errors in the mean. So for population 1, our mean was 9. We add 2 standard errors in the mean, and 2 times 1, of course, is 2. So the upper limit's going to be 11. And to get your lower limit, you're going to do the mean minus 2 standard errors in the mean. So that would be 9 minus 2, which would be 7. And voila, there's your 95% confidence interval. Now, luckily for us, the standard error, the mean, is the same for all 3 data sets. So for population 2, we're just going to start at the mean and go up 2 for our upper limit and down 2 for our lower limit. And from population 3, we're going to go up 2 from the mean for our upper limit and down 2 from the mean for our lower limit. Alrighty, so this is what your graph would look like. Now, looking at this graph, what do you notice about the 95% confidence intervals of population 1 and 2? That's right, these overlap. So what that means is that the true mean for population 1 could be all the way up there, and the true mean for population 2 could be all the way down there. So we can't, because those 95% confidence intervals overlap, we can't say for sure that there is a statistically significant difference between those two groups. So we would say the difference between these two groups, well, the data we have is inconclusive. Same thing if we look at population 2 and compare it to population 3, their confidence intervals overlap as well. However, if we look at population 1 and compare it to population 3, their 95% confidence intervals do not overlap. So we can say there is a statistically significant difference between populations 1 and populations 3. Now, if we go back to the question, which was right here, okay, this was a 10-point question, and part A was worth 3 points for creating the appropriately labeled graph with the axes labeled, with the units, trichomes per centimeter squared, and with the 95% confidence intervals. If you didn't put the units, I think the most you could get for the graph was 1 point. If you did not put your 95% confidence intervals, the most you could get is 2 points. Part B was worth 2 points. Based on the sample means and the standard errors of the means, identify the two populations that are most likely to have statistically significant differences in mean stem trichome densities and justify your response. So the two populations that would be most likely to have significant differences would be population 1 and population 3, because as shown in the graph we just did, the 95% confidence intervals for populations 1 and population 3 do not overlap. That would be the justification for your response. If you said 1 and 3 are the most different because their means were the most different, that was not an appropriate justification. They wanted you to use the standard errors of the means to justify the difference, and the 95% confidence intervals not overlapping. Okay. Now, part C was actually an experimental design question. Describe the independent and dependent variables and a control treatment for an experiment to test the hypothesis that higher trichome density in plants is selected for in the presence of herbivores. Identify an appropriate duration of the experiment to ensure natural selection is measured, and predict the experimental results that would support the hypothesis. So independent variable, there's a couple different ways you could do this. The way I would do it, independent variable would be the presence or absence of herbivores, herbivores being animals that eat plants. The dependent variable would be the mean height of the plants or the mean trichome density of the plants. Okay. The control would be the population without herbivores. You'd have to do the experiment for at least a couple generations to see how the population would change over time, and to predict the experimental results that would support the hypothesis. If over time the plants that grew in the presence of herbivores had a higher trichome density, that would support the hypothesis. Anyway, so that's a question that uses standard error of the mean and 95% confidence intervals. Hope that was helpful. Have a great day.